101, and this is number 33 here. And remember, the whole idea of Chapter 5 is mainly the topic about masses. How much does the atom weigh? And we'll certainly be revisiting that in Chapter 7 and Chapter 9 later, because that tells a lot about how much product you're going to get and all this and that. Now, on Chapter 10, we're concerned with the electron configuration, which tells us about reactivity and where the electrons go and all that. But at any rate, here we go, number 33. It says, the actual mass of one atom of an unknown isotope is 2.18 times 10 to the minus 22 grams. It says calculate the atomic mass, or the AMU, for this isotope. So someone flip in the back of their book there and tell me the conversion between atomic mass units and what? AMU equals, you see it there with the mass?
The kilograms?
Yep, there we go. What do we got?
1.6606 times 10 to the negative 27.
All right. So here's what we got. We have got that 1 AMU, and that's what we're looking for, right? That would be the mass of a proton. The mass of a neutron is this much. All right. So we got to get this in kilograms. So that means that we've got 1,000 grams is the same thing as a kilo, and that's going to cancel out. And I know now that there are 1.6606 times 10 to the minus 27 kilograms in one atomic mass unit. Now remember, the problem is looking for AMU. All right. Now, calculator, I've got it over here. So here's what we've got. We have got 2.18 times 10 to the minus 22 divided by 1,000 times, divided again by 1.6606 times 10 to the minus 27. That's going to be 131 atomic mass units. So what does that mean? Well, look in your periodic table and tell me what weighs around 131, approximately. What you guys got? Xenon. All right. She's telling me the noble gas xenon is the thing that approximately gets to this amount. All right. So if you had one atom of xenon, it would weigh 2.18 times 10 to the minus 22 grams. Now that makes sense, right? Because there's a whole bunch of atoms, all right, in a sample. So only one atom you would expect to not weigh that much. Are we good? Do which one now?
26.
Sure. Number 26. It says aluminum has an average diameter of about such and such. So, now this is number 26. All right. So the diameter of aluminum, okay, is 3 times 10 to the minus 8 centimeters. And the diameter of the nucleus is 2 times 10 to the minus 13 centimeters. And it says calculate the ratio of the atom's diameter to the nuclear diameter. Now what you can kind of see here is if you draw just kind of a rinky-dink picture, if you will, okay, this right here is your atom and this right here is your nucleus. Now one would predict that the nucleus would be considerably smaller than the whole entire atom, right? Which it is. I mean, take a look at this. This is minus 8, this is minus 13. You know, so that's 4 orders of magnitude smaller. 5 orders of magnitude, right? Been at it a while. 5 orders of magnitude smaller. Okay, so we want to know the ratio of the aluminum to the nucleus. Divide those two numbers. 3 times 10 to the minus 8 divided by 2 times 10 to the minus 13. Hitting the enter button for 150,000 times. What that means is if you look at any particular atom, you could put 150,000 of these little nucleuses inside the whole entire atom's volume. And remember, 99.99999% of the atom is empty space. But we're just saying if you could fill the atom with nucleuses based on size constraints. How many could you put in there? 150,000 of them. All right. That help you out? What else we got? Is that it? All right. Well, electrons. Well, you know, when you talk about electrons, the new way to talk about it is with your quantum statistical mechanics. And what that means is this, is electrons are all based on statistics. For an example, if any of you guys are married or have girlfriends or boyfriends or significant others or what have you, if asked this question, where are you at 2:15 on a typical Wednesday afternoon? Your answer would be what?
In here.
In here, in this room. Now, I can say that with something the statisticians call a 99.9% confidence level, or a 99 confidence level. Now, what does that mean? Well, that means this young lady here is always here. But she could step to the bathroom right now. I don't know. So if the observer was to look in this room, it is possible that they not find her. Are you with me? All right. But more than likely she'll be there. Electrons are the same way. You see, you can take electrons and we will put them in rooms for an analogy type reason. Okay? And when you put an electron in a room, it tends to stay there. Now, it's possible that it moves, okay, but it's not likely. You know what I mean? I mean, it's not very probable that it moves. Does that make sense? Okay, so now if you are an electron, I'm going to just walk over here. You can just keep the camera there. I'm just going to boot up the system here as I'm talking about this. When we're talking about the idea of electron configurations, what we're doing is we are trying to describe exactly where electrons are located. Because from a chemistry perspective, electrons are all about collisions, and they're called what are called grazing collisions. Now, let's just say that we've got an atom here that's got a nucleus. And then out here in these well-defined orbits, which we know is a bunch of nonsense, and I'm about to show you why in a moment, we've got electrons. Which one of these electrons would you predict would be doing the reacting? The outside ones, okay? And that right there is called a valence electron. And those are the ones that you really want to key into from a chemical perspective. Now, can these internal electrons react? Yes. Chemists can make that happen, but it is a very violent reaction conditions, okay? The same way, if me and Bonnie's going in the hallway and we touch each other, where are we probably going to touch? On our skin. That just makes sense, okay? Right? That's the outside skin electrons, the valence. It is unusual that I would touch her spleen or her stomach, right? Because that's sealed up in there. The same way with these core electrons sealed up in there. Now, violently I could touch her spleen. Think about it, right? You get a knife going and all this. But it's unusual that from a chemical perspective that I would. All right? So atoms are the same way. Whenever they react or molecules react, there must be some sort of a collision. And it turns out that every molecule has what's called, well, it's not called, I'm just making up a word, it's a sweet spot, okay? It's actually an energy type surface. And basically, not only do things have to touch, but they have to touch in a proper orientation. So every molecule sets up rules for that, by the way. So if me and Bonnie's a thing, our rule may be that my right shoulder must touch her left shoulder. Now see, if my right shoulder touched her right shoulder, then nothing would happen, see? We can only hook up with a certain surface. All right? So what's this chapter about? It's about examining where these electrons are. So later on in the course, we can talk about how these things are hooking up with these certain surfaces, if you will. Okay, so whenever you build an atom, what are you doing? Well, in using my analogy, we are going to build